Now to today's presentation. Today we are pleased to have Jennifer Hay joining us as our first presenter. Jennifer is a factory applications engineer with Agilent Technologies located in Oak Ridge, Tennessee. Her current responsibilities include training field application engineers and developing new applications. For our second presentation, we welcome Benoit Merrill of the Department of Materials Science and Engineering, University of Erlangen-Nuremberg. Dr. Merrill is currently working in research on nanomechanics of thin films and nano-indentation and bulge testing. All right, we are ready to begin, and it gives me great pleasure to welcome Jennifer Hay.
Hey, Rita. I'd like to begin by thanking all of you in our audience today. I sincerely appreciate giving these presentations, and so I'm grateful that there are people out there who are interested. Today I'm going to review an article that is frequently cited in indentation literature, and of course I'm talking about Ian Sneddon's landmark article published in 1965 entitled The Relation Between Load and Penetration in the Axisymmetric Boussinesq Problem for a Punch of Arbitrary Profile. I'm going to begin my presentation with Sneddon's motivation from a historical perspective. I'll explain the nomenclature. I'll review the boundary conditions for Sneddon's solution because they express the assumptions behind the solution, and these assumptions have to be respected when employing the solution. Then I'll jump right to the general form of Sneddon's solution, which applies to any axisymmetric body which is smooth at the edge of contact. Next, I'll show how Sneddon's general solution is applied for two specific situations of practical interest. The first situation is a cone in contact with a flat surface, and then the second is a paraboloid in contact with a flat surface. At that point, we'll move beyond Sneddon's work and look at the benefit of a derivative form of Sneddon's solution. Finally, I'll summarize and recommend a few articles that everyone should read if they're going to be working in the field of instrumented indentation. All right, when two bodies are in elastic contact due to a force, the force and the displacement are related through the elastic properties and the geometry of the two bodies. In 1882, Hertz was the first person to articulate this relationship between force, displacement, and elastic properties for contact between two curved surfaces. And in 1939, Love published an analogous solution for a cone contacting a flat surface. Then in 1965, Sneddon published a general solution governing contact between any axisymmetric body and a flat surface. And it turns out that the solutions by Hertz and Love are actually special cases of the Sneddon's more general solution. I'd like to point out that only Hertz assumed elastic deformation in both bodies. Both Love and Sneddon assumed that one of the contacting bodies was infinitely rigid. And now, in light of the fact that we ultimately want to apply Sneddon's solution to the interpretation of instrumented indentation data, I'm actually going to present a modified version of Sneddon's solution, which is informed by Hertz's understanding that deformation in both bodies can and should be accounted. So, in other words, I'm going to present Sneddon's solution, but with Hertz's approach of accommodating deformation in both bodies. All right. Here we have a schematic of two elastic bodies as they just come into contact. Body one here is a flat surface of semi-infinite extent, and body two here is a general axisymmetric body. Now, in the context of instrumented indentation, you can think of body one as the sample and body two as the indenter. The function f of r describes the original distance between the surfaces of body one and body two as a function of the radial coordinate r. Traditionally, the normal coordinates z1 and Z2 are positive into each contacting body. This schematic shows the same two bodies as they're pushed together because of a normal load P. The contact radius is A, and the total mutual approach or displacement is H. It's important to note that the origin of the system is right here, the point of first contact between the two bodies. Now, even as the two bodies are pressed together, the origin of the analytic coordinate system moves with this physical location common to the two bodies. The light dashed lines are the original profiles. So this is the original profile of the sample or body 1, and this is the original profile of the indenter or body 2. The deformation of each body is illustrated as the difference between the original profile and the deformed profile. The deformed profile is represented by the solid lines. For example, the red lines here illustrate the deformation of body 1 because body 1 started out looking like this, but ended up looking like this, okay? Started out here, but ended up here. Likewise, the blue lines illustrate the deformation of body 2, or the indenter, because body 2 started out looking like this, but ended up looking like this, right here. So the blue lines show the distance between the original shape of body 2 and the current shape, which is just the deformation in body 2. So this is the deformation in body 2, represented in blue. This is the deformation in body 1, represented in red. Now, let's look at the green lines. These illustrate the original separation distance F of R, right here. That's the distance between the original shape of body 2 and the original shape of body 1, which in this case is a flat surface. So why go into all of this? Well, the most important thing to note is that everywhere within the contacting region, the red plus the blue plus the green equals a constant value, or H, the measured displacement or the total mutual approach. In other words, the deformation in body 1 plus the deformation in body 2 plus the original separation distance is equal to the displacement. And actually, this is the first boundary condition in Sneddon solution. So here we have the same schematic as on the previous slide, and you can see that first boundary condition expressed right here. The deformation in body 1 at the surface plus the deformation in body 2 at the surface is equal to the total displacement minus the original separation distance. Now remember, Sneddon assumed that body 2, the punch, was rigid, so when you read his paper, you won't see this term here, but we are going to include it. The next two boundary conditions are easy enough to understand. There is no normal stress outside the radius of contact and no shear stress within the radius of contact. In other words, the contact is frictionless. I need to explain one more thing before presenting Sneddon's solution. Sneddon uses a variable transformation which normalizes the radial coordinate by the contact radius. The new radial coordinate is x, and it is obtained by dividing the original radial coordinate r by the contact radius a. So the picture doesn't look any different. It's just this makes the radial coordinate dimensional. So we start out with this radial coordinate, we divide by the contact radius to get this radial coordinate x. So by definition, the edge of contact is always at x equals 1. This transformation makes the math easier because the domain for x is just from 0 to 1. Okay, here is Sneddon's general solution for axisymmetric bodies, which are smooth at the edge of contact. I know this looks complicated, but you'll see the simplicity once we work through a few examples. We have an expression for displacement which only depends on geometry. So it only depends on geometry through this function f of x. Here, we also have an expression for force, which depends both on geometry here and on elastic properties here. And here, I've expanded the expression for E sub r to show how it's related to the Young's modulus of each body, here and here. Okay, let's look at a very specific, interesting example, a cone in contact with a flat surface. So for a cone in contact with a flat surface, f of r is just a line that passes through the origin and has a slope which is equal to the cotangent of the half-included angle of the cone. We substitute x times a in for r to get the same expression in terms of x, the dimensionless variable x. So f of x is just a constant times our dimensionless variable x. So the derivative of f with respect to x is just a constant. So we plug this in here, and so we use this expression for f prime of x, and that gives us a very simple integral, okay, which we perform and evaluate from 0 to 1. So the sine of what angle? The sine of what angle is 1? Well, that's just pi over 2. And the sine of what angle is 0? Well, that's just 0. So in the end, we have that the that this should, I'm sorry, there's an error here. This should be this is just fine. I made a mistake. So this is just fine. We have that the total displacement or mutual approach h is equal to pi over 2 times the contact radius times the cotangent of the half-included angle of the cone. Easy enough. So at this point, it's interesting to think about the contact depth, because the contact depth is just equal to our function f of x evaluated at x equals 1. Okay, so we take this function and evaluate it at x equals 1, and that just leaves us with this expression, f of x is equal to a cotangent of the half-included angle. And when we compare this contact depth to the total measured displacement, it becomes evident that the contact depth is to the total depth as 2 over pi. In other words, for a purely elastic, frictionless contact between a cone and a flat surface, the contact depth will always be about 2/3 the total depth, regardless of the absolute size of the indentation. All right, now let's turn our attention to Sneddon's expression for force. Of course, f prime of x is the same, and when we plug it into the generic expression, we get this definite integral here, which, when performed and evaluated at its limits, gives this definite integral. All right, we perform that, we evaluate it at its limit, and we get this expression for force. So when we apply Sneddon's general solution to the geometry of a cone in contact with a flat surface, we get this expression for displacement and this expression for force. We can know the direct relationship between force and displacement by algebraically combining these two equations to eliminate the contact radius A. And when we do that, we get this expression, which tells us that for elastic frictionless contact between a cone and a flat surface, the force simply goes as the displacement squared. Now, for reasons that are probably not obvious yet, we'd also like to know the derivative of force with respect to displacement, which is also called the elastic stiffness. So taking the derivative of P with respect to H gives this expression for stiffness. And finally, if we want to express the stiffness in terms of the contact radius, we substitute this expression for H and simplify to get this very simple expression relating the elastic stiffness, reduced modulus, and contact radius. All right, this slide shows all the details of applying Sneddon's general solution to contact between a paraboloid and a flat surface, which is exactly the scenario addressed by Hertz in 1882. Now, I'm not going to go through the solution step by step as I did with the cone, but all the details are here. I would like to point out a couple of important things about this analysis. First, the expressions for displacement and load are exactly the same as those obtained by Hertz, right here and right here. So the Hertzian solution is actually a special case of the Sneddon solution, which I think most people do not realize. What's really interesting is that Sneddon was apparently unaware of Hertz's work because Sneddon does not cite Hertz in his paper. So completely independently, they both came up with these same expressions for force and displacement for this particular geometry. The second thing I'd like to point out is that when you work through all the algebra, you get exactly the same relationship between stiffness, reduced modulus, and contact radius as we got for our cone, and that should really make you go, And on this slide, I've summarized the various expressions obtained by applying Sneddon's solution to the particular cases of either a cone or a paraboloid in contact with a flat surface. And indeed, even though these geometries are very different, the relationship between stiffness, reduced modulus, and contact radius is the same regardless of which geometry we're talking about. And this should make you go, because historically that's exactly what happened. Dr. George Farr, Dr. Warren Oliver noticed this identity in several particular cases, including these, and so they teamed up with a colleague in mathematics from Rice University, Dr. Franz Bratsen, and together they published an article showing that, in fact, this relationship holds. Stiffness is equal to 2 times the reduced modulus times contact radius. This relationship holds for any contact geometry governed by Sneddon's solution, and I've provided that citation here. So in summary, Sneddon's solution is so very useful because of its generality, not because it came first. It's cited so frequently because it holds for almost any contact geometry that is interesting for instrumented indentations. Earlier solutions by Hertz and Love are actually special cases of Sneddon's general solution. And for any contact governed by Sneddon's analysis, the stiffness is related to the reduced modulus and the contact radius by this overarching expression. Finally, I recommend that everyone working in this field should read these 3 articles at least twice. The great thing about reading truly original works is they don't presume a lot of foreknowledge, so they're not as inaccessible as you might expect. They're actually, all 3 of these articles are actually quite readable. So that wraps it up for me today. I'm happy to take a few questions before the next presentation.
And we would like to thank you, Jen, for a very interesting presentation. Ladies and gentlemen, I want to remind you that you may ask questions concerning this presentation by putting them in the Q&A box addressed to presenter host, or you may speak directly with our presenter by pressing star 1 on your touch-tone phone. Your line will be opened and you may ask the question in that fashion. All right, let me check our Q&A box and also our chat. It does not look like we have any questions at the moment. No? See, that's all I need to say, and then they come in. That's terrific. All right, the first question is, what if the indenter is not a perfect cone, but like a pyramid?
Well, the really brilliant thing is that analytically, this expression holds for any axisymmetric shape. It turns out, it has been verified experimentally over many years that this expression holds very well for shapes that are not axisymmetric, so long as the radius of contact is more generally understood. So that's so if you calculate an effective radius by taking the radius that would produce the same contact area that you actually have, then this expression still holds. So actually, the more familiar version of this expression, that the stiffness is equal to 2 times the reduced modulus times the contact radius, I think the more particular way that people are used to seeing that is that the reduced modulus is equal to the square root of pi over 2 times f over the square root of the contact area, okay? And that is just this very same expression solved for the reduced modulus and calculating an effective contact radius based on the contact area.
Thank you, Jen. Our next question, could you please repeat the integration from 0 to 90?
Yes, okay. I think so the sign, so this function is an inverse sine. So this is asking the sine of what angle gives you 1. So you would put the 1 here for x, and the sine of what angle is 1? Well, that's just pi over 2. Then the sine of what angle is 0, and that's just 0.
All right. Can you give a real example of when this model breaks down?
That's a really excellent question. This model, let's go back to the boundary conditions, actually, because I think that's the right way to answer this question. Okay, so these are the boundary conditions that are used to come up with this solution. One of the boundary conditions, of course, is frictionless contact. And so as you move away from that assumption, as this equation becomes less and less relevant. So that would be one situation where this breaks down. I haven't gone into in this presentation, I haven't gone into specifically how this equation is applied when you have plastic contact. I think to some extent, Benoit is going to address that. But certainly, if you have substantial friction, you're going to get away from the applicability of this equation. And one of the ways that you get substantial friction is by using a very sharp indenter. Okay, when you use a sharp indenter, you are more apt to be adversely affected by friction. If you use an oblique indenter, such as a Berkovich or a flat punch or a sphere, even if there's significant potential for friction, the force resolved along the interface is a lot less. And so even if there's potential for friction, you aren't particularly well bothered by it. So when you have friction, Stenn's equation is less applicable. And then the other place it would break down is if this is not quite true. There was an important publication by Farr, Bolshakov, and Hay, and that's actually my husband, Hay, that's not me, Hay, where they showed that this particular boundary condition is not entirely adequate for modeling physical indentation experiments, and they propose a very useful slight modification to Sneddon's stiffness equation based on that observation. So if anybody's interested in that reference, I'd be happy to provide it. But I would say those are the two situations where it's most likely to break down.
Thank you. We'll take one more before we move to the second part of our presentation. On the figure in slide 7, can you show what exactly is the contact depth, the red one or the red plus blue?
The contact depth isn't particularly identified in this slide. The contact depth would be the distance from the bottom of the green line up to the edge of contact. It's actually not called out in this figure. Rita, I have a question that came in on the chat. You said that it's questionable to use this equation for sharp indenters. What is the form used for Berkovitz indenter? It's not questionable. It's always used for sharp indenters. It's just cleverly applied to the unloading curve, which is a purely elastic curve. So you have to be clever about how you're applying it, and that's actually the focus of Benoit's presentation. But the use is not particularly questionable. It's very common.
All right, thank you. There are a few more questions which we will address at the end of the second presentation, but for now I would like to introduce our second presenter, and that is Dr. Benoit Meyer. And if you will bring up your presentation, we will begin.
Yep. Thank you very much, Rita, and good morning or good afternoon to everybody. It's a pleasure for me to deliver the second presentation, which will hopefully give you further insights into the contact stiffness, and especially the contact stiffness during unloading. So this research has been performed at the Institute for General Material Properties of Matthias Göken here in Erlangen, Germany. And I'm greatly indebted to my co-workers, Verena Meyer and Carsten Durst. So before we start, I would like to introduce the effective indenter shape concept. That is a concept that has been introduced by Farr and Bolshakov in 2002. It is basically consists into an equivalence between the real situation where an indenter is removed from a plastically deformed surface, and the ideal case, the virtual ideal case, where a virtual indenter of slightly different shape is actually pushed onto a flat surface in a purely elastic way. So of course the second situation is easier to account for. Specifically, you can better understand the shapes of the unloading curve, and you can calculate, well, you could calculate more easily the stress field below the indenter. The issue with the effective indenter concept is, of course, that its shape is at first unknown. So Farr and Bolshakov proposed to start from the load displacement data acquired during an indentation to perform a fit of the unloading with a power law function here, which gives access to both parameters A and M, which are the fitting parameters, and they actually describe the shape of the effective indenter thanks to those two values according to the equation they provided in their paper, and that you can see here. So that's not the easiest equation I know, and I will show you in the rest of this presentation that there is another way, more simple way, more natural way to get access to the effective indenter shape. But first of all, I'd like to come back to contact stiffness. You have heard a lot about it in the previous presentation from Jennifer High. I wanted to stress once more that this was a very important parameter for the Oliver Farr evaluation method that is commonly used for evaluating nanoindentation experiments. indeed, it is present in almost every equation of importance. If you want to calculate, for instance, the contact depth, hc, you need the stiffness, s. If you want to calculate the hardness, you also need it, prove the contact depth. And lastly, you would need it to calculate the Young's modulus, well, the reduced modulus, ER. So how to measure the contact stiffness? Well, you can measure it at the beginning of an unloading. That is to say, at the point here of maximal displacement into surface. This you can do by sticking to the original definition of the stiffness. So in this case, the stiffness at that point is the local slope, of the unloading load over displacement curve. Well, of course, you're doing a single measurement, so you will get a single value of the stiffness that is only valid at the beginning of the unloading, and as a consequence, you will only get the value of the hardness and modulus at this given depth. If you want to get further values at different depths, you have to perform further loadings with multiple partial unloadings, or you have to apply you have to use the CSM option that Agilent introduced some 20 years ago. CSM stands for continuous stiffness measurements and consists into overlapping, basically superposing a very small and fast oscillation to the master loading curves. And thanks to the multiple partial unloadings, it is possible to calculate the stiffness almost continuously and to get continuous values of the hardness and modulus over the indentation depth. And what we have now done is that we have extended this continuous stiffness standard method in order to keep this small oscillation going over the whole unloading segment. And thanks to that, we can also measure the stiffness during the whole unloading, and we hope to gain supplementary information thanks to that might have been overlooked before. So how does it work? Let's take now an example of an indentation in fused silica. Well, it starts with a loading that is actually performed just like in the standard Agilent CSM method. As you can see here, the contact stiffness is continuously increasing, and it just means that the contact area is also increasing over time. Well, after the loading, we used 30-second hold segments. So depending on the material, you will observe some creep or no creep. Well, here it is with fused silica, so the creep is very limited. And last but most important, we performed the unloading in a new way. Well, not only did we let the CSM oscillation on, but we also performed the unloading in an increasingly slow pace so as to better capture the increasingly fast changing contact area. Well, as you can see on this plot, it is actually not possible to get the stiffness signal for the very last moment of the unloading, after 98% of the unloading, because the indenter loses surface. Okay, another interesting observation is that the very beginning of the unloading looks pretty linear, and well, this is actually indicative of a purely elastic deformation, and I will come back later to that. So for the time being, we have recorded the contact stiffness S over the displacement into surface H during both loading and unloading. It's a bit difficult to understand this first curve, so we decided to change parameters and to switch to parameters that we could physically better understand. So instead of the contact stiffness S, we represented the contact radius AC, which is actually the contact stiffness divided by a constant. That's the that's the meaning of the stiffness. The stiffness is indicative for the magnitude of the contact. And instead of a displacement into surface, we chose to represent the contact depth as calculated according to the Oliver-Farr equation. So that is the resulting plot here to the right. Interestingly, the beginning of the unloading is now overlapping the end of the loading. And I will also come back later to that. For the time being, let's concentrate on the loading sequence. What happens during loading? When we press an indenter on the surface, it actually creates a sinking of the surface around the indenter. That's what you can see here. It's usually called HS. And what you can also see on the schematics is that you can describe the contact between the indenter and the material by defining the contact radius, AC, here, and the contact depth, HC. So the contact radius, AC, is readily calculated by the Sneddon equation, and it is actually what we have been plotting as the x-coordinate on our plot. And the contact depth, HC, is actually given as the difference between the overall indentation depth or displacement into surface and the sinking of the surface around the indenter, HS. So the equation is provided by Oliver and Farr. It is H minus epsilon times the load over the stiffness. And that's what we have plotted as our y coordinate. So if you now compare the schematics here with the experimental plot, you will reach the conclusion that what we are observing here is nothing else than the shape of the indenter. And indeed, if you measure the angle here more closely, you will find the characteristic 70-degree angle of the Berkovich indenter. So now let's turn to the unloading sequence. Here the situation is a bit different because after a certain point, when we remove the indenter, the residual indent will emerge from the side of the indenter. So this band of material, which is represented here above the contact depth, is not the elastic sinking any longer. It is actually the elastic sinking plus a plastic component. And if we want to describe the contact in the middle of the unloading, we have to modify the equation that we used previously, the so-called Oliver-Farr equation. We have to introduce this new unknown parameter, H imprint. So this equation here describes pretty well what's happening during unloading. Unfortunately, that's not what we have been plotting here. Here we have been plotting the Oliver-Farr contact depth, that is to say this equation, but without the H imprint. So what we are seeing in the left diagram as the y-axis is not the actual contact depth of the indenter. But let's now try to remember the concept of the effective indenter. I told you in the introduction that the definition of the effective indenter was that it was a virtual punch, elastically pressed against a flat surface. This also means that the effective indenter is fully qualified for the application of the Oliver-Farr equations, which means that the contact depth of the virtual effective indenter is actually obtained by the equation that we have plotted as the y-coordinate. And what we are seeing in the left diagram is nothing else than the shape of the effective indenter pressed on top of a virtual flat surface. So that is quite amazing because the effective indenter is virtual, doesn't really exist, it's virtual. And still, it appears directly into the measurement data. So now let's sum up a bit. By recording the loading stiffness, we could directly get access to the shape of a real indenter. while by recording the unloading stiffness, we got access to the shape of the effective indenter. What we can now do is to compare both. And if we do that, here on the left figure, on the right figure, we will see that it is possible to get a representation of the residual impression. So this is, if you remember the equations that I've presented in the previous slides, you will reach the conclusion that the new parameter H imprint is actually the difference between what we measured during unloading and what we previously measured during loading. So that actually H imprint is directly the difference between both curves. So back to our example with fused silica, I just plotted the difference between both curves in the diagram below, and what appears is the residual imprint, the profile of the residual imprint. So that's quite practical because you can tell directly from your indentation data without need for further imaging afterwards. We applied the new method to different materials. We took sapphire, which is actually a common reference material for nanoindentation because it doesn't show any pileup. We took nanocrystalline nickel and ultrafine grained aluminum because they have grain sizes that are small compared to the indentation depth. So the materials can be considered behaving microscopically isotropically. However, both showed some creep during the whole segment. So if we now look at the measurement, we can see that those materials that have very different mechanical behaviors also show different behavior of the unloading stiffness. You can see that the decay of the stiffness is extremely fast for mostly plastic material, while it is more slow and it's more curved for sapphire, which is a bit more elastic. So of course, we calculated the shapes of the corresponding effective indenters. Well, they can be extrapolated to 0 as previously. And anyway, what we can see is that clearly the larger the amount of plasticity in the material, as for UFT aluminum, for instance, the smoother the shape of the effective indenter is. As for UFT aluminum, it's almost a flat punch. While for material like sapphire or fused silica with a high elastic recovery, the shape of the effective indenter is it's sharper and a bit more like the shape of the real indenter, actually. So we also calculated the corresponding residual impressions, and I also plotted as the dotted line the maximum penetration of the indenter as a comparison. And once more, we can see that materials that behave more plastically get a very flat residual impression shape compared to the more elastic ones. Last but not least, we performed a comparison with the predictions from the Farhan-Bolshakov model. So I've already introduced the equation. It is actually it requires the parameters M and A, which are obtained by fitting the whole unloading segment of the load displacement data. This is somehow equivalent to measuring the contact stiffness during the unloading. So we can see on the diagram that both methods agree well, quite well. Well, that's quite excellent for sapphire and fused silica, while there is a small discrepancy for nanocrystalline nickel and UFT aluminum. I believe this is because those materials show some reverse plasticity during unloading, and since the Farhan-Bolshakov model is actually based upon a fit of the whole all unloading. And since the curvature of this unloading will be affected by this reverse plasticity, actually the far Volchenkov model could be affected. And this is not the case of a new method, where the stiffness is actually measured from the CSM signal from a very fast oscillation at about 70 Hz, where no reverse plasticity can take place. So the advantages of the new methods are that it provides a direct measurement without complicated equations or complicated theoretical background, and that the result will not depend, for instance, on the fitting equation that you have chosen or on a time-dependent effect of the material. And last but not least, the new method allows a comparison between the measurements that are performed during loading and unloading, and this gives access to the topography of the residual imprint. We have also extended the method and extended the ideas that I've developed before to the experimental determination of epsilon infused silica. So epsilon is a parameter that is repeatedly used in the Oliver Farm method. As you can see here, it's necessary to calculate the contact depth, the elastic modulus, and the hardness. And the value that is used is often the literature value of 0.75. And here we wanted to see if there was a natural way to measure this epsilon value. So if you remember the plot of the contact depth over the contact radius for fused silica, you will remember that I mentioned that the end of the loading segment and the beginning of the unloading segment were overlapping. So this is actually due to the fact that fused silica is an extremely elastic material, and that the surface that the material at the outskirt of the indenter is purely elastically deformed, so that the surface reforms at its original height after the end of the unloading. So of course this diagram was calculated with the literature value of 0.75, and you might wonder what happens if we use another value. So this we have done. Here is one single measurement performed in fused silica. That's an indentation with 8 partial unloadings, and it has been evaluated 3 times with 3 different values for epsilon. And as you can see, the loading and unloading overlap only, should overlap only if the right value of epsilon is used. So we extended this ID, we performed more measurements, and we performed such a kind of best fit procedure. And at the end, we could determine that for the value of 0.76, we had better agreement between loading and unloading. This value of 0.76 is an excellent agreement with the literature, and the advantage of our new method is that it's a purely experimental result without need for any theoretical background at all. However, you can only apply this method to very elastic materials. So I would now like to conclude. I hope I could convince you about the interest of measuring the unloading stiffness. Not only does it provide us with a direct measurement of the effective indenter shape, but by comparing it to the stiffness recording during loading, you should also be able to get a representation of the topography of the residual indent. And lastly, we used the new methods, the measurement of the unloading stiffness, in order to justify the value used for epsilon in the Oliver Farm method by a purely experimental way. So if you're interested in more details, you're welcome to read the article that we have just published in JMR. And lastly, I would like to acknowledge the help of Eric Herbert for complementary measurement and the funding from the German Science DFG within the Cluster of Excellence Engineering of Advanced Materials. I thank you all for your attention, and I would be happy to answer your questions.
And we would like to thank you, Dr. Merrill, for an excellent presentation. And yes, we will get to the Q&A session in just a moment. But for now, I would like to ask our audience to complete a brief survey. The poll is now open on the lower right side of your console. Please complete each question, and we thank you for taking the time to answer this survey. We do value your opinions on how Agilent can better serve you, and we welcome your feedback on our presentations. And as you're completing the survey, I'd like to remind our audience of the way they can be asking questions, both of the first presentation by Jennifer and of the one that Dr. Merrill just completed. You may ask questions by putting them in the Q&A box addressed to presenter, host, or you may ask questions directly over the phone line by pressing *1 on your touch-tone phone, and you will be connected into the main conference, and you may speak with our presenters. All right, so that we do not waste any time with the questions that we have, we would like to try to get to all of them. Let me see, where is this? The first question is, and this is for you, Dr. Merrill, can the technique be used to determine the extent of pileup?
Well, unfortunately not, because you need the value of, well, I can go back. Well, you basically, to calculate AC, you need the value of a reduced modulus. And if you have pileup, you will not be able to calculate reduced modulus reliably. Oh, let's take that, yeah. It was better. Yeah, when you calculate AC, you need the reduced modulus ER. And if you have pileup, you will not be able to calculate reliably ER.
All right, and why is
well,
this?
To a certain extent, of course.
Oh, excuse me.
Yeah.
Our next question, why is the slow unloading curve above the loading curve, unlike the conventional linear unloading?
Which slide is that?
It doesn't refer to a slide.
Wait,
but it came in just as you were beginning the presentation, so I'm assuming that it is concerned with your presentation.
Can you read the question again, please? Rita?
Sure. Let me go back up. Why is the slow unloading curve above the loading curve, unlike the conventional linear unloading?
Ah, okay. Now I see what it means. Yeah, that was at the beginning. That's for fused silicon. Let's go back. Yeah, here. Oh, I think we had it bigger. Exactly. Well, what happens between this point here and this point here is that you have had some supplementary deformation. Well, what can happen during creep here, you can see there is a small displacement, is that actually the displacement into surface stays the same, but the contact stiffness increases. So this means that your indenter stays at the same depth, but the contact area increases probably because the elastic pile up around the indenture is slowly converted to some plastic deformation. That's what I could. That's how I could interpret it.
Thank you, Merle. Let me just check our phone queue. Diane, is there anyone in the queue?
I'm showing no questions in queue.
Thank you. We have a question in the Q&A box, and Dr. Merrill, if you will look at question 2, I will read it. It's a rather long question, and I'm thinking that perhaps it would be easier for you if you were able to see it yourself, and I'm not sure if you see it. But at any rate, let me go ahead. What is the typical amount of shear stress over volumetric stress applied into the isotropic flat surface through such mechanical contacts? Can we consistently rely this separation of deviatoric and dilatational stresses to the type of indenture shape? And my apologies. I'm not only losing my voice, I'm having a little pronunciation problem. Do you see that question?
Yeah, I can see the question.
Okay.
Well, I would say it depends on the material. I would also say that's a more general question that does not directly refer to the present research. I don't know if Jennifer has some.
I can't see the question.
Oh, okay.
Unfortunately.
Well, I'll remind our audience, if in fact we are not able to get to all of the questions today, we do send the questions and the answers from our presenters through the Q&A log via email. So the questions will be answered. Let me go on to this question. First of all, a comment, good work. As the effective indenture height was found using the slow rate unloading stiffness, how can we determine it is independent of the rate of unloading?
Well, once more, it depends on the material. I mean, so let's go back to 20. Yeah. Well, we performed actually the measurements with different unloading rates, and we could not see any difference for fused silica and sapphire. However, there were some differences for nanocrystalline nickel and UFG aluminum. And this is partly because of elastic recovery during unloading, and also because the contact area change rate is extremely high for those materials. So there is some technological challenge into measuring this with VSM.
Thank you. And you mentioned it depends on the material, Benoit. This question says, if you change the materials you indent, do you measure a different value of epsilon?
Well, as I mentioned earlier, the determination of epsilon was only possible for very elastic material, and in this case, fused silica. We did not try it with other materials.
All right. Well, and the next question you just answered. Have you tried to measure epsilon on other materials than fused silica? So that one, with that answer, you answered 2 questions. All right, let me check the chat box again. We're just a little over our time, but in the meantime, I want to just mention to our audience that following the seminar, you will be receiving a email once the recording is posted on the Agilent website, giving you the link to the recording, as well as a link, as well as a copy of the PDF of the presentations themselves. And I'd like to call your attention now to the slide presently displayed. If this is a new Nano e-seminar coming up on May 24th. If this topic appeals to you or your colleagues, we encourage you to go to our website to register for it. All right, before we close down here, let me check one more time to see if we have any further questions. And it appears we do not. As I mentioned, we will be sending the log with answers to all the questions via email. We do appreciate your attendance as well as your participation in this seminar, and thank you for your time. We hope to see you at the May 24th seminar. And for now, though, we'll close the phone line. We will leave the presentation open for any further questions or feedback. And from Agilent Technologies, we wish you a good day.